this is something that's a little bit interesting, although it has kind of limited use. Because when you're dealing with parametric equations, this is only going to work if we're looking for area bounded by the curve and some sort of horizontal axis like the x-axis. So we can't do this for areas bound between two curves like we used to do for just rectangular functions. So here's one thing that we could do. Suppose we have a parametric graph and we're looking for the area between the graph and the x-axis, as you can see, right over here, and one thing that we can think of is still, if I'm going to look for the area of this region, I can still split it up into little rectangles. And what I know is no matter how this graph gets, created, it's not y as a function of x, but I know that every single point up here, no matter what this is a y value. So y was plotted, right? The height of this rectangle is some y of t value. Right? And then we have to worry about our little delta x. So that's y of t times some delta x. But the question is, what's this delta x? I would like it to be in terms of, t. So that what I do know about x of t is that it is a function of t. And what I can use is this. I can use this differential notation. Delta x is equal to x prime of t times dt, right? So dx, so the differential bit is dx is x prime of t times dt. So if I want to find the area of this, well, what I can do is just find the sum of all of these. I'm going from t sub 1 to t sub 2, and my formula is going to be y of t times x prime of t dt. So you can try that with some parametric curves, and you can also verify it by changing those curves back into rectangular form, and you'll see that you get exactly the same thing.